In this video, we're going to look at the relationship between white light and color by recreating a portion of Newton's Prism experiment, as presented in a letter to the Royal Society in 1671. But first, a little bit of background. At the time of his experiment, the prevailing theory was that white light was a color of light, and that other colors could be created by modifying the white light somehow. For instance, this red piece of plastic would be described as changing this white light into red light. They also had knowledge about how light behaved at the boundary between two materials. For instance, at a planar boundary, they knew that the ratio of the sine of the angle on each side of the boundary was fixed for a given set of materials. We now know this is a form of Snell's law, where the ratio of the sines of the angles is equal to the inverse ratio of the refractive indices of the materials, where the refractive index of a material is related to how fast light propagates through it. This expression allows us to predict what will happen at a planar boundary as we change the angle of incidence, and it also allows us to deal with more complicated shapes, like this triangular prism. It's just a matter of geometry and keeping track of the angles. Newton was working on designing lenses for telescopes when he decided to investigate the phenomena of prismatic colors. Those are the colors that occur when you pass white light through a prism. So he obtained a triangular prism, and he passed some white light through it, and he saw a rainbow, just like he expected. But then he noticed something. In the direction that the colors were spread, the pattern was much wider than it should be based on the system geometry if light obeyed this fixed sine ratio law. So he did some experiments. He separated out individual colors in the spectrum and passed them through additional prisms, and what he came to realize was that all of the colors in this spectrum are their own form of light, and they all experience a different refractive index on traveling through these prisms. So this led him to the conclusion that the white light entering the prism wasn't really white, it was a combination of all these different colors, and that all the prism was doing was separating them in an angle by this varying refractive index. This is an interesting conclusion, but it doesn't really prove what's happening because we're still relying on this prism to make these colors. So what we really need is an experiment where we can form these colors from white light without a prism, and at the end of his paper, Newton suggests just such an experiment. You start with the same system you had before, and then you place a lens in the system. We start with our screen close to the lens, and we see the same spectrum we saw before. Here is the light passing through the lens, and up above it we see the light that's sort of skipping the top of the lens. As we move our screen away, the colors begin to overlap until at one point we see a band of white light. As we continue to move the screen further away, we see the same spectrum that we started with, but with the colors now reversed. As we move the screen in this experiment, there's nothing to cause this change of color that we're observing. The only thing that's changing is the overlap of the colors. So we can conclude that when we perceive this white light, what we're really seeing is a whole bunch of colors added together. Now it turns out that you don't actually need all of these colors to trick your eyes into seeing white. If you're watching this on a TV screen or a computer screen at home, what you're seeing as white is actually a combination of red, blue, and green. But for our purposes, we're seeing the sum of all of the colors in the input spectrum. Okay, that's pretty neat. We start off with white light, we form a spectrum of color, and then we use a lens to combine it back into white light. But it only really combines it into white light at one spot. If we go further away from the lens and closer to the lens, it's still clearly a spectrum. So is there a way to combine this white light so that we get a beam of white light sort of like we had at the input? It turns out the answer is yes, but it's a little bit more complicated than you would expect. So a lot of books draw this system where we start with our original prism and we put a second one in, something like this. And to our eyes this looks like it's working, but it's not really. All that's really happening is the light hasn't had enough time to spread. So it looks like it's white, but if you had a very sensitive instrument you'd be able to tell that there's a change in color across this. And you can see it more clearly by eye if we place this prism further down. Over here, it's clear that there's a change in color across the width of the beam. If you really want to make a beam of white light from this colored spectrum, you can follow the method outlined in Newton's Optics. This comes from his last experiment in Book 1. You start with a prism that we had before. Then you add a lens to the system, and you want this length to be roughly twice the focal length of the lens. At some distance away from the lens, we'll put another prism, and this distance again should be roughly twice the focal length. And we adjust the prism, and what we see is a reasonable approximation of white light. Now you really should build this system with a much larger focal length lens and should build a much wider system to get a really good separation between these colors here and a very clear white beam at the output. But for this video, this will work. Thank you for watching. I hope you found this material interesting. If you'd like to learn more about Newton's optics experiments, I'd recommend two resources online. One is the Project Gutenberg, where you can find a copy of Newton's book, Optics, and the other is the Newton Project, where you can find a copy of most of Newton's papers.